we're going to discuss a shortcut method for finding n of t in two space. So recall our original strategy. We start with r of t, and then we construct t of t, which was velocity divided by speed. And this one wasn't so bad. But then n of t was what? N of t was t prime of t divided by the magnitude of t prime of t. And that can get pretty challenging. There's a lot of calculus to do there. So the previous example that we have done was this parabola. So we have r of t is t comma t squared plus 1. So we can certainly get t of t. That's not very difficult. So the velocity v of t is r prime of t is 1 comma 2t. And the magnitude of the velocity is the square root of 1 plus 2t times 2t, 1 plus 4t squared. So again, t of t is velocity divided by speed, which gives me this. Velocity 1 over square root of 1 plus 4t squared. And 2t over the square root. Again, that computation's not bad. And from this, we can see that t of 1 is 1 over root 5, 2 over root 5. And what is r of 1? R of 1 is 1, 2. So from this, we can go ahead and look at our graph to visualize the unit tangent vector at that point 1, 2 on this parabola. So let's go ahead and put in a vector field, a space curve, r of t. So we have t squared plus 1, and 0 in the z direction. And we're going to take a look at that in the 2D world. And I'm interested in the vector. So we go ahead and add the vector here. The vector is 1 over root 5, 2 over root 5. 1 over square root of 5, 2 over square root of 5. 0. And where does that occur? That occurs at the point 1, 2. So this should be our unit tangent vector. Let's go ahead and make it red and see it. And let's zoom it out once so we have a little bit larger region to consider. So now ask yourself this question. What is orthogonal to that red vector with length 1? How many choices would you have? If your goal is to construct an orthogonal vector to 1, 90 degrees, and it's got to land in this plane. Remember, this is a two-dimensional strategy, so the shortcut method works in two space. How many vectors of length 1 do I have orthogonal to the red vector? Well, there could be one pointing this way, and there could be one pointing that way. Now, how do we find out what those possibilities are? Well, let's think about it. I have my t of 1 here. So what is one of my possibilities? We'll call it n1 of 1 is a possibility. I have to switch the x and the y because I need to get a dot product of 0. So I'll put 2 over root 5 here and 1 over root 5 here. And I have to change one of the signs because right now this is positive and this is positive when I multiply them, and the dot product wouldn't be 0. So let me go ahead and make that one negative, and let's see if what I get is a normal vector, and is it the unit normal vector for that vector valued function at that point. So let's go take a look, see where we are. So I'm going to add another vector, which is 2 over root 5, negative 1 over root 5. And 0. And let's go ahead and make this one green. And it occurs at the point 1, 2. Is this orthogonal to the red vector? It is, but is that the unit normal vector? What are we told? The unit normal vector needs to be on the concave side of the graph. It has to bend around the unit normal vector. This thing is bending away from the normal vector. So this is not the unit normal vector. Well, what else could I try? Do I have another possibility? Well, what would a second possibility be? Remember, we switched the x and the y and changed one of the signs. So the x moves over to y. The y moves over to x, and I change one of the signs. Well, I change the second sign here. I'm going to change the first sign here. So what I have is -2 over root 5 and 1 over root 5. Might that be the normal vector for this vector valued function at the value 1? Let's take a look. So coming back here, I'm saying this green one originally was no good. That green one was 2 over root 5, -1 over root 5. Let's make the first one negative and the second one positive. Might that then give me a vector valued function that we want? And sure enough, it does. So this version is the normal vector. It is length 1. It is orthogonal to the red vector t of 1, and it is on the concave side. So from that, we can conclude what? We can conclude that n of 1 for this is -2 over root 5, 1 over root 5. And that's going to give us some guidance to figure out what n of t is. So here's the information that we've collected so far for this shortcut strategy. We have r of t, we have t of t, we have t of 1, and we have n of 1. Now, what do we need? We need t of t and n of t to be orthogonal. So their dot product has to be 0. So t of t is 1 over root 1 plus 4t squared, 2t over root 1 plus 4t squared. So n of t, how am I going to get n of t? Think about that for a few seconds. I need the dot product with big T to be 0. So the strategy that we use for our example is the same. Switch the x and y and change one of the signs. So y moves here, becomes x. X becomes there and becomes y. And I have to change one of the signs. But I did that work with n to tell me that I had to change the sign of the first component. So this will be my formula for n of t.